Welcome to Bryan Research and Engineering's webinar on AP-42 tank emissions in ProMax. My name is Stacy Diefenbach. I'm part of our support group here at BRNE, which means that anytime you have questions about anything at all, whenever you call us or email us, you might get to hear from me. Some of you, it looks like I've helped before or taught before, so welcome to all of you. If you're new to ProMax, welcome to you as well. A little bit about me. I graduated in 2013 from the wonderful University of Oklahoma with a degree in chemical engineering. I've been at BRE ever since, so about 7 years now, and air emissions has been kind of one of the things that I've focused on and had a lot of work over the years. In this webinar, we'll define the emission types we'll be looking at, discuss EPA's AP-42 documentation a bit, including some of the major updates, major changes between the 2006 version and the latest 2020 version. And we'll explore how to easily model all of that, all the new calculations in ProMax. First, we'll take a look at the different types of storage tanks that we have in ProMax in AP-42 documentation. We have fixed roof and floating roof are the main categories. For fixed roof, there's vertical or horizontal. Floating roof, we have external, internal, and domed external, with a few other pieces in the middle of those. So those are different types of tanks we'll be looking at. For the emissions that we're looking at, the first type that we'll discuss are flashing emissions. So flashing is the instantaneous vaporization as the pressure drops to atmospheric, as we have liquid coming into our atmospheric storage tanks. That is AP-42 Chapter 7.1 honorable mention because it does mention flashing losses, but it doesn't give us any calculation methodology for doing so. In ProMax, we calculate it based on the equation of state that's been chosen and some binary interaction parameters that we've fit by collecting data on hydrocarbons and their solubility in various compounds for over 40 years. So in addition to just the equation of state, we use some modifications to that to better match reality from the theory. We also have working or withdrawal losses. These are in AP-42 Chapter 7.1. What we're talking about with working losses is any vapors that are pushed out of the tank as liquid fills fixed roof tanks. So typically you'll have a fixed roof tank, there's some amount of liquid in there and there's some amount of vapor space on top. As you fill more liquid into that tank, you're going to push some of that vapor out, and that's what we call those working losses. Withdrawal losses are for floating roof tanks, and basically as liquid is pumped out of the tank, some of the liquid clings to the sides of the tank and to fittings inside of that tank and evaporates, and that's what we call withdrawal losses. We also have breathing or standing losses. This is also in AP-42 Chapter 7.1. As the temperature increases throughout the day, the temperature of the liquid of the tank will also increase. And as that liquid temperature increases, we do get some vaporization that happens in that liquid. So this is the breathing of the tank throughout the day. As it gets hotter, it breathes vapor out. Or standing losses is another word for this. As it's standing there throughout the day, we have some amount of losses. We also have loading losses. This is in AP-42 Chapter 5.2. These loading losses are vapors emitted from tanker trucks or a loaded vessel as liquid fills it. So these tanker trucks or the vessel that we're using to transport, they're not held at vacuum. That would be very expensive and difficult to do. So what we do is there's some amount of vapor sitting in there from whatever was in there last. And as we fill that with liquid, we're going to have that vapor being pushed out of the truck or that vessel. All right, does anybody know what AP-42 actually stands for? I didn't, so I looked it up. This actually came from a report in the Environmental Health Theories. It was called a compilation of air emission factors. It was a Public Health Service publication number 999 AP-42. So the AP actually stands for air pollution. It was a general subject area. The others being radiological health, RH, or urban and industrial health, UIH. And 42 is that publication number. So that's where it all comes from, and it's stuck around all this time. The very first edition of this was in 1968. All that covered in terms of tank losses was gasoline storage tanks at refineries only. It had one emission factor for cone roof tanks and one emission factor for floating roof tanks. That was it. It had 76 total pages, and there were 3 pages on storage tanks. The second edition came around in 1973. That separated gasoline and finished products and crude oil. It also further expanded to different emission factors for breathing and working losses of fixed and floating roofs within a table. So still emission factors for everything in a table, relatively short and sweet, but a bit more information than was originally published. The third edition was in 1977. This is where we got the basic framework of the API equations that we now know and love. It was a little bit shorter. There was only one long equation for the different types of emissions. It also included some accuracy estimates. So for fixed roof working losses, it said it may deviate significantly. No accuracy estimate was given. For fixed roof breathing was plus or minus 10% for that single equation. Floating roof standing losses had plus or minus 25%. Floating roof withdrawal losses, no estimate of accuracy was given, but it was derived from gasoline data, and it said applicability to other stored liquids was uncertain. Loading losses had a single equation, and it was plus or minus 30%, and that's very close to what we have today in loading losses. The fourth edition was similar overall equations to the third edition, but it did add guidance on how to actually calculate things like molecular weight and vapor pressure instead of just having those in the equation. And it gave much more detail on floating roof tanks, including adding a separate internal floating roof equation. The fifth edition came out in 1995. This has most of the updates that we're used to seeing. The original 1995 version, this is officially Chapter 7 and Chapter 5.2. It was much more similar structure to what most of us have seen now. The 2006 update had the addition of vent setting correction factor, that KB factor for fixed roof working losses, and it also added a wind speed dependent factor for rim seal losses in floating roofs. The 2019 update is what is big news for most of us now. Some previous equations were using defaults, and what they determined was that now that everybody has computers, we can use a lot more detailed equations and get more accurate results. And we'll look through a couple of those here in a second. The 2020 update was mostly minor typo fixes. There weren't very many major updates to that version. So I do want to spend a little bit of time going over some of the major differences between the 2006 and 2020 versions, since that's what's currently affecting many companies now. And we'll walk through a couple of those together. This is by no means an exhaustive list. This is just what I consider some of the most important pieces from what I've seen. One of the big differences are temperature equations. So in the 2006 version, in this case, we're looking at the average daily liquid surface temperature, TLA, but this does apply to many different types of temperature equations that are throughout that AP-42 documentation. In the 2006 version, there were 4 variables and some constants. So you can see that's a relatively easy equation. In the 2020 version, we go to 7 different variables, plus some constants, plus a lot nastier looking equation. This does simplify down to that previous equation if the shell solar absorptance equals the roof solar absorptance, and if the height to diameter ratio is 0.5. That was an assumption that was being made throughout a lot of the previous AP-42 documentation, 2006 version. So what that means, if the shell height to diameter ratio is 0.5, that means for a vertical tank, if it had a height of 10 feet, it would have a diameter of 20 feet, which may be true for refineries, but most of the time for our production facilities, that's quite a bit different. That's a lot wider than what we typically see in the production facilities. So generally, having that H/D of 0.5 results in a larger surface area, and that typically results in a higher liquid temperature, which generally gives you higher emissions. So by adding this HS/D term, if you have a production facility or a tank that is not twice as wide as it is tall, typically we'll get some lower emission numbers from this because it doesn't heat up quite as much with less surface area across the top. All right, a few more updates here. We have the option in the new version to have uninsulated, partially, or fully insulated tanks. Previously, uninsulated were the only equations that were really given. Partially insulated tanks mean that the tank shell is insulated, but the roof is not. And fully insulated tanks means that the shell and the roof are both insulated, and it's assuming that it's being maintained at some constant temperature because of that. The vapor density equation also changed. Previously, TLA, or that liquid surface temperature, was being used in the vapor density calculation. That's been replaced by the vapor temperature, which makes sense. If we're trying to figure out the density of the vapor, we should probably be looking at the temperature of that vapor as well. This has been in the API documentation for a few years now, but we hadn't had an update to AP-42 until recently, and those were applied here. We also have additional tank conditions. Previously, we had good or poor paint condition for your tanks. That's rather subjective. I could say that I think my paint looks good enough, but may not be exactly what they intended. So they've renamed them and added a new piece. So new is the same thing as good in terms of the numbers, but they now have a definition for what new is, and that's that paint still retains the fresh shine. Old is the same number as what we used to consider poor, but old has the definition now of paint is faded and dull. The addition is the average, which is just the average of those two. And the definition for that is the paint is in good condition, but the initial shine has faded. The suggestion is typically to use average unless it's been freshly painted or is definitely old and dull. We also have the addition of the annual sum of the increases in liquid height. So that's for the working loss equation, and those units are feet per year. So how many feet did increase over the course of the year? If you know this number from pump records, you can use that. If you don't know that number, you can use the old regular throughput, the total throughput, and the volume of the tank to determine what this number would be. If you actually know the sum of the increases in liquid level, there will be a lower, what we call net working loss throughput, if you're pumping in and out at the same time, which would lower emissions. So what that is saying is if you're pumping in and out at the same time, you're not going to be changing that liquid level quite as severely, and so you're going to have lower working emissions because you're not actually increasing the level by as much. I had a question on how much does the tank condition affect the results, severely or mildly? It does depend on what else you have and what composition you have. Typically, in one case that I looked at, it's a couple tons per year out of 15. So it can be significant. The paint color is much more important than the paint condition, typically, from what I've seen. Good question. The working loss equation has changed from 2006 to 2020. We're looking at the 2006 version here. The other things that have changed are the number of turnovers, how that's calculated, and also the working loss turnover saturation factor, or that KN. So the working loss equation having changed does have an impact. I think the bigger impact can be that KN and N have changed. So what that KN factor is trying to show is that if you have a high number of turnovers, that vapor space in your tank is probably not completely saturated with whatever you have coming into the tank. So for a high number of turnovers, you had a reduction in this KN factor, it'd be something less than 1, and it would give you lower total emissions, which makes sense. In the 2020 version, we have a couple differences. Notice N has changed. Previously, it was just the throughput over the max volume, and this time we're looking at some of the increases in liquid level and the maximum and minimum liquid heights. The KN equations themselves have not changed. It's still the greater than or less than 36, but they've added this piece that says for tanks that are vapor balanced and tanks in which flashing occurs, KN equals 1 regardless of the number of turnovers. Which also does make sense. If you do have flashing happening in that tank, whenever you get any new liquid going into that storage tank, you're going to have vapors that are emitted, and that vapor space is going to be saturated. What I've seen from this is sometimes a very drastic change in your emission numbers. For very large tanks with high number of turnovers, what previously had a KN of 0.3 is one that I've seen in the 2006 equations, now has a KN of 1 because there's flashing occurring at the same time. And so what that really does is that triples your overall working emissions, because as you can see in that 1-35, it's just a straight multiplier on that equation. So if you had a KN of 0.3 and now you have a KN of 1, that's a very significant difference between those. So that's one piece that I've seen make a really big impact on the emission numbers. If you had a relatively low number of turnovers or had small tanks with low throughput, probably not as much of an issue, but it can be a very big change. For floating roof emissions, we now have the summation of rim seal, deck fitting, and deck seam if you have internal floating roof tanks. All of those are summed up to equal standing losses. Previously, all of the losses were just summed up with the withdrawal losses for the total routine losses. But now they've broken out anything that's not withdrawal losses and called it standing losses. So just the categorization is a little bit different. There have been temperature equation updates similar to what we saw in the fixed roof, where we have that HS over D and the shell and solar absorbance being different. We also have the withdrawal losses using annual throughput or some of the decreases in liquid level, which should be equal to some of the increases in liquid level if that number is known. Previously, the withdrawal losses used tank capacity times annual turnover rate. So in this case, we're taking out that number of turnovers and using throughput or the sum of decreases in liquid level. For floating roofs, using the annual throughput, if you're pumping in and out at the same time, is not quite as much of an overestimation as it would be in the fixed roof because we have a little bit more control with those floating roofs. We're going to jump into the ProMax side of things. I like to get my simulation green and solved before I start trying to get fancy and put on specific equations. And so that's where we're going to start here. So to start, we'll specify fully our process here. This is an atmospheric storage tank at the end of a production facility, is this example that we're looking at. We've cut off the rest of the production facility just to make it a little bit easier, so we only have to specify our atmospheric tank. So we have our pressurized liquid coming in. For those of you that have played in ProMax before, or anybody that's been to my training classes, you know that you need 4 things to fully specify a ProMax inlet stream. Typically, that's composition, temperature, pressure, and flow rate. So composition I've already set here. In this case, we do have a C10 plus fraction. We can do that in ProMax. I'm not going to cover the details or the specifics of that here, but if that's something you're interested in and you're not sure how to get it, let me know and we can help you get that set up. So we have our composition set up here. So we still need a temperature and a pressure. We're going to assume this comes in at, say, 150 degrees from a heater treater or maybe a stabilizer. And our pressure is going to be 22 psig. So enter in those pieces of information. I did mention we need a flow rate. How often do we know the flow rate entering into our atmospheric storage tank? Not very often, right? Typically, what is the flow rate that we do know? The condensate, right? So if we go to the condensate stream, do you think we can set a flow rate in the condensate and have ProMax calculate what the inlet flow rate is? If I'm asking, the answer is probably yes. So we can go into that condensate stream and we'll say that we know our outlet flow rate was 188 barrels per day. So we'll set that. And then we need to set the conditions for this atmospheric hydrocarbon tank. I like to set my conditions in the flash gas stream. So that's where I will set mine. And we're going to set this identical to the conditions of the location that we'll be looking at in the stencil here in just a second, the tank losses. So I know that that temperature is 80.45 degrees Fahrenheit and 14.4 psia. With that, everything should turn maroon. And again, for those of you that may be new to ProMax, maroon is a good thing in ProMax. We are based in Bryan, College Station, home of the Fighting Texas Aggies. So maroon is a good thing. Maroon means it has everything it needs to solve. It just needs to be executed. So I'll click execute flow sheet, turn everything green, and then we can jump into the tank losses portion. I already have a tank losses stencil pulled out onto this sheet here. If you need to find it, it's in the ProMax Air Emission stencil. If you don't see that, you can go to more shapes and find the Air Emission stencil. I have a bunch of different versions because I play with this a lot in the different versions and I do a lot of testing for the different pieces. So yours would only have one, and you can grab the ProMax Air Emission stencil. We have both the 2006 and 2019, which is essentially the same as the 2020 versions here. For the 2006 version, so far as I'm aware, currently for inventory, if you did your permits with the 2006 versions of the equations, I believe most states are still allowing that to be used for your inventory. Because there are some changes that can make significant differences, it's not really fair to penalize you just because the equations have changed. Many states are requiring that all new permits be done using that 2019 or 2020 version of AP-42 equations. But for the 2006 version, that may still be required for legacy use or for those inventory purposes. Once we click and drag out a tank losses shape, it will ask us to select a piece stream. And we want to always select the inlet to the tank. Previously, you could do either the condensate or the pressurized liquid, although we've always recommended using the pressurized liquid or the inlet to the tank. But because of that additional language in that KN factor, double checking to see if flashing occurs, we have to have the inlet of that tank so we can see if flashing occurs before we do the rest of the calculations. So it needs to be the inlet stream, in this case, the pressurized liquid. Then we'll say OK. And then it'll bring up some information that we can put in about our tank. If you notice on the flow sheet in that message box, it will tell us what we still need to specify. As we specify more information, that message will change. And once we have everything, it'll be happy and we'll be able to solve it. But if you can't get it to solve, can't get numbers to appear, take a look at the flow sheet and it'll tell you what is still missing to help you out. We are going to use a vertical cylinder in this case, but you could choose all of the different types of tanks here. Our shell length is going to be 25 feet. Shell diameter is going to be 12 feet. So in this case, instead of that height to diameter ratio of 0.5 that was assumed before, we have a height to diameter ratio of 2. So very different numbers there. The number of storage tanks employed, we're going to say that we have 3 tanks in this battery. Be aware that we are doing the calculation the same way for every tank. So we're assuming that it is filled and emptied the same exact way for each of these 3 tanks. Part of the inputs are the maximum and minimum and average fills of that tank. And so if it's different between those different tanks, your numbers may be different. So when you say 3 tanks in the battery, we assume they all operate identically. Then we can pick a city. We have a big long list of cities available. So this is just for the meteorological data for each of those cities. I'm going to use Dallas because that's my hometown, Fort Worth, and because I can. If you don't like the options that are available there is an option for custom location. If you choose custom location, you'll have the ability to set your maximum minimum average temperature, your pressure, solar insolation, wind speed. So if our locations are not close enough to where you are located or where your site is located, you can definitely feel free to set your own as well. You can do a time frame of a year or any of the individual months. If you choose the individual months, you will have the data of meteorological data for that particular month. So July will be hotter than, say, January. So if you need to do ozone season calculations, you can choose those months. And you can hook this up to Scenario Tool, for those of you that are familiar with it, to do some case studies of different months and how that affects your emissions. The report components, by default, it's the non-exempt VOCs, which is the normal VOC list, minus anything that is considered exempt, like methane and ethane. We also have non-exempt VOCs and methane, since methane has become a bigger talking point as of late. If you'd like to see it with the addition of methane, you can. And then all, which will sum up all of the components for those totals. We'll leave ours as non-exempt VOC here. Set bulk temperature to stream temperature. We're going to skip over this for just a second. We'll come back to it towards the end. That is for if you have high temperature feeds coming in and we can't necessarily assume that we reach average temperature in the tanks. What is the basis for ProMax climatological data? Good question. So we have compiled the new AP-42 table of all of those places. We've also grabbed information from the original AP-42 or the 2006 version of AP-42 and the tanks 4.09D, since they had additional meteorological data that wasn't in the AP-42 for the 2006 version. So we've taken all of that meteorological data and put it into ProMax. So we've grabbed it all from the EPA or from the documentation given for those. So we haven't pulled any random ones ourselves. But I've also been told that NOAA can be used really easily as well. So if you want to put in your own, that's completely fine. But ours is all from the various EPA documentation. Yes, you can use Scenario Tool to view emissions for each month for all the months in the year. So basically in Scenario Tool, you could tell it to run through all the different months and then sum them up in Excel at the end. And you could see all the individual ones. And if you're interested in that, let me know. That's a little bit outside the scope of what we're going to look at today, but it is definitely a very powerful tool that we can help you get set up. The next checkbox is use AP-42 routes vapor pressure. That is what AP-42 explicitly says to use, is Raoult's law to calculate vapor pressure. This is an ideal situation. It looks at ideal gas. It's looking at the summation of the pure component vapor pressure times the mole fraction of that component in the process. And so it is not probably terrible for hydrocarbons that are all mixed together. They're probably fairly similar. There will be some additional interactions that happen that it's not taken into consideration. But for a hydrocarbon tank, it's probably not horrible. However, for a water tank, Raoult's law should not be used. Again, Raoult's law is for things that are similar to each other. And how similar are water and oil? How well do they mix? Not really at all, right? So we suggest, especially for water tanks, unchecking that AP-42 Raoult's vapor pressure. And then we'll look at the oil that's sitting on top and what the properties of that are and how that will vaporize in the system as well. In the response to comments, EPA did say that in AP-42, the fact that they used Raoult's law was not meant to supersede all other available options for calculating vapor pressure. So in my personal opinion, I think ProMax's thermo is better than Raoult's law because it does take into consideration the different interactions of the different hydrocarbons and what likes to stay with what based on real data. So my suggestion would be to uncheck that all the time, but it's not required. And oftentimes that will give you slightly higher emissions if you uncheck using Raoult's law because of the way the hydrocarbons interact together. So Raoult's law is accepted, and that's what a lot of people choose to do. But if you have a water tank, we highly recommend unchecking that option. Someone asked, how sensitive are the calculations to the meteorological data? That determines the temperature profile inside of the tanks. So that is extremely dependent. The emission calculations are extremely dependent on where it's located and what temperature ranges we're seeing. That's why the different months also make a big difference. August is going to have much higher emissions than January or December. So it does make a very big difference what you choose. If they're a couple degrees off, probably not going to cause massive changes. But all of this is dependent upon what the bulk temperature is, what the liquid surface temperature is, and all of those things are determined based on the temperature and the sunshine of the location that's selected. So it is very important to make sure you have a decent location and good data for that. Next, we have the maximum, average, and minimum fraction fill of tank. We'll leave ours at 90, 50, and 10. Material category, we have to choose between light organics and heavy crude. Unfortunately, AP-42 does not tell us which is which. It just says if you have light organics, use this multiplication factor. If you have heavy crude, use this factor. TCEQ typically recommends an API gravity of 40 degrees being the cutoff. So if you have an API gravity higher than 40, then you'll choose light organics. And in this case, our API gravity is 71, well above that 40-degree cutoff point. So we will choose light organics for our material category. You can choose your various insulation levels here. We're going to leave ours as uninsulated. And tank color, ours is going to be medium gray. So you have tank color and also the roof color. They can be separate. So we'll have medium gray for both, and we'll use average paint condition for both as well. Our breather vent and vacuum pressure we'll leave at the default. AP-42 says if you don't have better numbers to use, you can use plus or minus 0.03. So that's what we'll leave at ours. But if you have better numbers, feel free to put that in instead. Our roof is going to be conical, so you can choose dome or cone. If it's a dome, you will need to give us the radius of that dome. If it's a cone, we'll need to have the slope. AP-42 does say if you don't have a better number, you can use 0.0625, but we know that ours is 0.05. Flashing temperature. So we talked briefly earlier about the fact that flashing is not really detailed in AP-42. So it doesn't say what temperature you need to use for flashing. It just says flashing happens, and then here are the equations for the working and breathing and everything that happens afterwards. So our default is to use the maximum liquid surface temperature based on the location that you've selected. That is a little bit on the conservative side, probably. That's the hottest temperature it could ever be based on the annual average. So it's looking at the entire year average. So 80.45 degrees Fahrenheit. If you were looking at only July or only June, it was very hot here in July. So I know that the max temperature that it was sitting at was not 80 degrees. It was probably closer to 90 or 100, depending on the day out here. So that is something that you can choose. You can select whatever you would like to use for it. It does have to be higher than the bulk temperature, or at least equal to the bulk temperature. You can't have a lower temperature flash than what's sitting in your tank, because as soon as that tank is at whatever bulk temperature, the flash is going to occur at that temperature. So the only requirement that we have is it has to be higher than the bulk liquid temperature in the tank. Our default is the maximum liquid surface temperature. The question is slope just rise over run, or does it use pitch? I believe it's just rise over run. I would have to go double check actually in AP-42 to see what that is. If you have bolted or riveted construction, you can check that on. It will change some pieces of the calculation because it's not quite as tight fitting as some other options. If you have a known sum of increases in liquid level, you can check that on and tell us what the sum is in feet per year. If you don't have that value, then you can leave it unchecked and we'll use your throughput like we did before in 2006 with, of course, the changes to the equations that have been applied for the 2020 version. But if you don't know the sum of the increases in liquid level, that's fine. You don't have to set it. If you have a vapor balanced tank, typically vapor balanced tanks refer to underground horizontal tanks, which oftentimes are at gas stations, not oftentimes at production facilities, but there is some writing as to what to apply if you have a vapor balanced tank. So we do have that option here as well. But for most of the time, that generally won't apply to what you're looking at. You can choose to calculate loading losses and output the various types of losses. If you uncheck calculate loading losses here, we have specified everything we need to for the working and breathing and flashing. And so that will appear on our flow sheet. All right, to calculate loading, we need a little bit more information, and we can see that it's asking for some additional information on our flow sheet. We've been looking so far at the working and breathing parameters tab. To the right is the floating roof fittings tab. So if we chose a floating roof, all of this would be available to specify. We do choose the defaults that AP-42 says if you don't have better numbers for this, you can use these. But then you can go in and individually change and set all of your different fittings and internals for those floating roof tanks. In this case, we have a fixed roof tank, so we don't need to do any of that. The next tab over is the loading loss parameter. So we need to tell it how we are loading and what we are loading. In this case, we're going to be loading a truck, and we are going to have submerged loading with dedicated vapor balance service. Then we need to give it an overall reduction efficiency. So we're going to assume ours is 68%. What that is an average of two different efficiencies. We have a capture efficiency, so that's 97% in our case for the vapor recovery equipment. And then there's a vapor collection efficiency, and ours is going to be 70%, so it's the average of those two. A truck not passing the annual leak test has a 70% vapor collection efficiency. So it's a combination of two efficiencies that we get our overall reduction efficiency from. A good question, how are gas blanketed tanks handled with the model? Is there any special setup or considerations needed with the parameters? In the new AP-42, it actually says specifically that for gas blanketed tanks, you don't need to do anything different with the calculations. If you really wanted to, you could add a second inlet for whatever normally is used for that gas blanket. You would have to have a flow rate of some sort, and it will slightly change the composition of what's happening inside. So if you'd like to do that, you can, but AP-42 specifically says you don't need to make any different accommodations for that. It should be negligible in the overall calculations. The maximum hourly loading rate, if you want to set this, you can, and we will calculate the max loading, but this is just a straight unit change here. We're not doing the TCEQ's short-term emission calculations. It's just using a different flow rate. We'll do the loading loss calculation again using your maximum flow rate, but that's not using the worst case temperature and the worst case vapor pressure, those types of things. That is hopefully going to be added. We're working on a block that does some of that and improves some other user interface pieces of this. So that is coming in the future, but currently that maximum hourly loading rate is not the short-term emissions as you'd see from TCEQ. So just be aware that that is a different value. It's just the regular loading equation with whatever flow rate you tell us here. All right, we have the results tab to the right, one more. This will tell you kind of what the meteorological data we have that we're using and the different types of losses and what they are. So we have the atmospheric pressure, the maximum liquid surface temperature. So that's for that 80.45 and the 14.4 that I got earlier to put into that flash gas stream. And then we have the individual losses per tank, and then the summations of all of those broken down here. We also do have a working and breathing report that will tell you the working, breathing, and total with the compositions, same with loading and flashing. If you had the max hourly loading rate that you would set, we would calculate, again, the same loading equations with that new throughput here, and flash report as well. All of that is within the stencil. There is one more piece that I think is useful. To the right of that stencil, or on the right-hand side, we have some words if you zoom in. One of them says flashing, one says working, breathing, loading, and residual. All of those are stream connection points. So if I draw a stream from each of those, I can get the composition and flow rates of all of those things in a stream, which then you can report like normal in a ProMax report. You could also grab that and send it somewhere else. If you want to send it to a combustor, get 98% destruction efficiency on that, you could. The question, our short-term loss is basically all the losses except breathing and standing. So the short-term is actually mostly like the loading equation, just with worst case numbers for temperature. It's usually 95 degrees or the actual temperature, whichever is worse. And it's just a separate documentation. It's based on the AP-42 documentation, but it's slightly different. It does give it in terms of hourly emissions, I believe. The modifications to it are estimates. In AP-42, it does explicitly say that you shouldn't be using AP-42 calculations for anything less than a month. But there's estimations from TCQ on the short-term worst case, and that's typically worst case loading is what it's based off of. So we'll name our streams, because if anyone's been to my classes, I like naming everything, otherwise I'll forget what I was doing. This also makes reporting a lot easier. If you name everything nicely, you won't have reports for streams 1 through 5. You'll have reports for your flashing and working and breathing streams. This residual is the residual liquid after flashing, working, and breathing have happened. So that's the liquid that you should be loading into your truck. So you can double click on any of these, and they are just regular ProMax process streams. You may see a little bit odd pressure in these streams. The reason for that is that AP-42 doesn't care about mass balance, and AP-42 doesn't care about vapor and liquid based on composition. So ProMax automatically tells you whether the given composition you have is a vapor or a liquid or a combination of both. Because AP-42 doesn't take into account thermodynamics at all on that side, it's just a bunch of equations that you're plugging numbers into for averages on an annual basis or maybe a monthly basis. So oftentimes the composition that comes out of that, especially when using Raoult's law, is a mixture of vapor and a little bit of liquid, but it looks a little bit strange to have liquid coming out the top of your tank or coming out in your emissions for flashing. So what we do in ProMax is we make sure that the mole fraction vapor is 100%, make sure that it's all vapor, the flow rate is still correct, all the compositions are still correct, but we just let pressure float be whatever it needs to be to make sure that we have 100% vapor in our air emissions. Typically that's going to be a vapor stream. So that's why you may see that pressure a little bit different when you look at the streams off the side. That's just, again, because AP-42 doesn't take into account detailed thermodynamic calculations. But again, the flow rates, the compositions, all of that is exactly what you need to see. You can look at this in mass flow of tons per year if you want to look it up on a component by component basis. Get all of that information for each of your different emission streams. Good question. Are there any options for specifying a tank is top filled or bottom filled and how that affects the flashing? There is not currently. We assume that everything is in equilibrium. If you do have filled from the top, you're probably going to have some additional splashing. My recommendation would use a more conservative temperature for that flashing temperature, and that will offset some of that, but there isn't any data given for how that affects it in a dynamic way, because that will depend on how fast the flow is, how much it sprays, how much drops and creates more droplets, how full is your tank, how far does it have to drop. So there's a lot more complicated pieces that come with that and actually figuring out how much more would vaporize. So in this separator that we're looking at here, we're assuming it's at equilibrium at the temperature and pressure conditions that you've set. So I would recommend setting a slightly higher temperature to account for higher flashing that you'll have from that splash loading. Another question in the simulation is the flash gas stream effectively all the tank loss results from the AP-42 equations. So this flash gas stream is only for flashing. And the only reason it's identical to what we have in this flashing stream from the stencil is because we have the temperature and pressure set identically. So again, AP-42 doesn't care about thermodynamics. It doesn't care about mass balance. Based on just the equation itself, it is possible to have more propane emissions than you have actually entering into that tank just because of the way it's written. So we would never, in our process simulation side, when we're modeling facilities, we would never suggest people use AP-42 to use that to figure out what the flash is that's going farther down into the process, because it's not really that detailed. So the separator in ProMax is assuming equilibrium and it's just doing a flash. It's not doing working, breathing, and standing and loading. So this is just the flash, which is why we always use the stencil and use those streams coming off of the stencil as opposed to whatever you have in the ProMax separator. The only stream that this actually needs to solve is the pressurized liquid. I've thrown on the tank here really just for show and for us in this case to back calculate how much flow is actually coming in since we only know the outlet. But we really only need one stream for the tank losses shape. This separator could be used in any process amine sweetening, it could be used in dehydration, it could be used anywhere else in the full process models, and we wouldn't want to use AP-42 for all of those things. Good question. Since we let pressure float, how does that affect the compositions? It does not. It does not change the compositions. We are just floating pressure to make 100% vapor, but the compositions are set by what's happening in AP-42. So the compositions don't change on a mass or molar basis. If you're looking at actual volume instead of standard, standard is nearly always used because it's consistent. So if you're given a volumetric flow, it's almost always in standard volumetric flow. And again, pressure will not matter for that. So if you were looking at actual volumetric flow, that would make a slight difference. The pressure change here is so small, it wouldn't be much regardless, but the physical properties and the compositions won't be affected by doing that. All right, we had one piece that we skipped, and I said we'd come back to, and that's this set bulk temperature to stream temperature. TCEQ in particular has a requirement that if you have a high temperature feed for your tank, you can't assume that we get all the way down to atmospheric temperature conditions. What they consider a high temperature feed is anything over 100 degrees Fahrenheit. In our case, we have 150 degrees Fahrenheit coming in to our tank, and we're saying right now that it gets down to 80 degrees is the maximum liquid surface temperature, which may not be entirely true. If you're constantly filling from 150 degrees Fahrenheit, you're probably not going to get all the way down to just the annual average temperature. It's probably going to be a little bit warmer than that. So what we can do is we can set the bulk temperature to stream temperature, check that box on. You'll notice that the flashing temperature changes, as does the bulk temperature. So this is again setting the bulk temperature. We're saying the bulk temperature is now 150 degrees based on what's coming in. There are some different equations within AP-42 that determine what the maximum liquid surface temperature is compared to the bulk temperature. So we use that to determine what the new maximum liquid surface temperature is. And again, that is the default that we have for the flashing temperature. That's still probably quite high. Most tanks are filled from the bottom. And what that means is as you fill the liquid from the bottom, it has to bubble through any liquid that's sitting in the tank. And there will be a temperature gradient that happens as it goes up, and there'll be some that liquefies or stays liquid before it actually comes out in the flash gas. However, it is probably true that we can't get all the way down to atmospheric conditions. If this is the case, if you have a high temperature feed, what we suggest doing is show the valve that is actually here in reality. On the ProMax side, we're assuming that you have a valve directly in front of this atmospheric tank that actually drops it down to our atmospheric pressure. Our pressurized liquid comes in at 22 pounds. You're not going to be trying to feed 22 pounds into an atmospheric tank. Typically, those are rated for about 16 ounces or 1 pound. So trying to blow in 22 pounds of your pressurized liquid is probably going to blow a hole in the side of your tank. So typically what actually happens is we have a valve directly in front of it that drops the pressure, and then it enters the tank from there. So if we do that, and you remember PV equals nRT, as we decrease our pressure, what is temperature going to do? Also decrease, right? PV equals nRT, so it's going to track with our pressure. And so by adding in the valve here, we can tell it to drop pressure first. And I'll set exactly the same 14.4 psi-A. And we'll execute. So if you saw before, our working and breathing losses were something close to, I think, 19, flashing was maybe 30, and now it's 31 and 190, so we're much higher. Right now we're still looking at that pressurized liquid, so before we drop the pressure, if we change our stream, which is the very top option here, there's a dot, dot, dot you can click on to change which stream you are selecting. And if I now choose stream 1, which is the new one I created, we go down a little bit from 180 to 138, which is quite a bit better, from over 30 to under 30. So it's still much higher than it was originally before we had that set bulk temperature to stream temperature, but it is a little bit more reasonable now. And this is, again, how it actually happens in the field. You'll drop the pressure first, and so you get a little bit of reduction. Instead of 125-degree flashing temperature, we now have 119, so that's what makes the difference. And just as a look-see to what we had before, so we're at 29, 138, and 6. Without the set bulk temperature to stream temperature, we're down to 17, 10, and 4. So it does make a big difference when you have those higher temperature feeds, but that's what that set bulk temperature to stream temperature option is for. All right, we'll look at one more thing here. You can create reports in ProMax. We do have one specifically for tank losses in general. We've created a custom report for this setup. There is a report button in ProMax, which is surprise how you do reports. If you click on the report button, it'll bring up a new window, and you can set a whole bunch of things, but in this case, I have a template that I've created to make this easier. So you choose the template output type, you'd say OK, and then you'd find the template that you saved. In this case, just to save you a little bit of time watching things happen, I've already created the template. This is from before we did the set bulk temperature to stream temperature, but this is what the report would look like. So we have a title page with a report summary of our VOCs, butex, and H2S. All of the sums and the breakouts of those different types are available. We have a picture of what it looked like on our actual flow sheet. The inlet stream summary, so this is what was set on the inlet stream, what our various temperature, pressure, flow rates, composition was. We also have the inputs to our tank losses shape, so which tank loss stencil you're looking at. So if you have multiple, if you have a water tank and a hydrocarbon tank on the same page, this would report for both templates or both tanks. And all the various inputs that we had, the material category, number of tanks, the maximum average liquid height, whether it was insulated, the different colors, paint condition, cone or dome, vent and vacuum pressure, all of that information that we put in, meteorological data as well. So it gives you a breakdown of all those pieces. And then the last one is a more detailed report of the emissions on a component by component basis. We still have the summations, total per tank, the different stream properties that we have for each of those, and the different stream mass flow for the different tank inlet, flashing losses, working, breathing, loading, residual, total emissions, all of that information in a nice, pretty report here. So if this is something that interests you, please let me know. Again, you can shoot me an email when I put it up here in just a few minutes, and I can send you this to use for your own models. And it's a little bit easier than trying to find all of the different streams that you want. We have it all broken out in what we hope is an easily readable format. Any questions on any of that? Has the simulation been vetted by EPA as being a true reflection of AP-42? I have worked with EPA, and we've worked with several states to actually come up with this report template to see what the different states want. I've talked with EPA as to going through this, and they've all said it makes sense. I have, myself and a couple of my colleagues have gone through in Excel calcs and verified that it's identical to what the equations say they should be. So we're very proud and confident in the numbers that come out of this. And if you'd like to double check it, you can, but it has been done several times, and there are many states that accept this, many EPA members that I've taught and shown how this works, and we've never really had a problem with anybody questioning the validity of it. It does depend on what you put into it. If you put in a bad composition on the inlet, that'll make a difference for sure, but the actual AP-42 equations, we're confident are what they should be. Is it easy to revise the basic template? It is doable, and I have a guide that I can send you if you're interested. Depending on how much you want to revise, we can do some of that for you. Again, it's doable, but there is some sort of pseudo code in the background that if you're not familiar with programming at all, it may be a little bit more difficult. It's not true code. It's more VBA and an Excel code, so it's doable, and there is a manual for it that I can send you, but we can also help make some minor modifications as well. With this setup change, if you're trying to run a scenario for all of the sites in one run, so if you have a scenario tool, the nice thing is in scenario tool, you can call a report to be made for every run if you'd like. So if you have 10 sites to run, you can set it up, put all of your different inputs in, your different tank specifications and colors and throughputs and compositions, put all that in as inputs. And one of the things that you can also have ProMax do is as scenario tool runs, after it finishes, it'll create a report of whatever run it has just done. So for that site, and you can either append those all together in a single document in Excel, or you can have it create a separate Excel document and just put it in a specific folder. So as it runs, it'll create a report at the end of that you can then go review. The TCEQ requires using either 95 degrees or the tank liquid surface temperature, whichever is higher, for tank working breathing short-term emissions. And how do you change the temperature used for working breathing short-term losses? So we don't currently have an explicit short-term emissions portion in there. What you could do is you could set bulk temperature to stream temperature and set that to be a higher temperature. It's not exactly the same because it's bulk temperature versus liquid surface temperature. But since, especially for fixed roof, it's really just one equation. You can pull the numbers you need out of ProMax and then do that equation, because you can find very easily in a stream what the vapor pressure at 95 degrees would be. And you can plug that in, since it's really just one equation with a few inputs for that one. In the next version that we're hoping will come out soon, it's being currently worked on, currently being tested in-house. We will have a specific section for the short-term emission losses as per TCEQ's requirements. You'll be able to set whether it's 95 degrees or the temperature. It'll do a check for you, and you'll be able to set that temperature if you want it to be something different. Is the tank emissions tool available to purchase as a separate standalone module from ProMax 5.0? Unfortunately not. It all comes included. Part of the beauty of ProMax is the free support and all of the engineers who work on the support side and everybody who works in development. It's all just one big group, so it's really hard to break out how much exactly that would cost. One thing I want to mention is that E&P tanks and tanks 4.09D, I know many people have used those in the past. They are not being updated any longer, so the 2020 updates are not in those modules, but there are still legacy uses for those. Like I said, for inventory, those can still be used, typically speaking. Just one more thing I want to point out here. Back in 2010, Marathon Oil published a study of emissions from a tank battery in the Bakken Formation, which compared the emissions predicted by various simulators with those measured in the field. ProMax wasn't initially included in that study, but they did publish their data, the oil composition and the process conditions, and so we plugged it into ProMax just to see where it would fall. And we've recreated the image just to make it a little bit easier to read. But this is what all the data points said. So you can see those white circles are the data points, and those blue lines are where ProMax fell. So take that for what you will, but just know that we do work very hard to make sure you get good results if you put good information in. Again, we've been collecting solubility data for hydrocarbons for 40 years, and we use all of that data to modify the theory to better match reality. So we're very confident that we have good results for you whenever you put in good inputs. And my information is now up on the screen. So again, feel free to email support with any questions you have, or you can email me directly. Our number is down there at the bottom, 979-776-5220. We don't have any automated voice answering system. You will talk to a real live person, and you can tell them exactly what you need, who to talk to, or if you want sales or want support or you want me in particular, just tell her what you need and you'll get sent the right direction. And thanks for tuning in, and hopefully we'll see you next time.